All right. Hello, Black Hat. I'm so happy to be here with you today. Welcome to my brand new talk, which is Who Cares Where Waldo Is? Locating macOS users without their consent. This is a kind of fork of my previous research already shown at Black Hat. So before I had 3 Black Hat talks about bypassing macOS privacy prompts, the TCC framework. But in this brand new talk, we're gonna focus only on location services. So you will see why I separated it from the TCC. My name is Wojciech Reguła, and I'm a head of mobile security at Securing. I'm an author of certified iOS application security engineer course for developers and pen testers. I will, tell you about it later at the end of this talk. I'm mostly focused on macOS and iOS application security, and I document all my findings on wojciechreguła.blog. Actually, I have a small delay because currently I have 65 already registered CVEs in Apple products, so there would be a lot of blog posts, so I have a delay, I'm sorry, but in the end they will be there, I promise, maybe. So the plan for today's talk is that I'm gonna introduce you to, or remind you, how TCC works and what are the privacy fundamentals on macOS. Then I will tell you a bit about location services because that's a separate framework, let's say, separate service, separate daemon, separate database. So I need to show you the difference on how the permissions are stored, etc. And then we're gonna focus on attack surface for location services, which in the end will lead into 5 categories of vulnerabilities that I already found, and they are all fixed by Apple, of course. I don't want to show you any 0 days in here. However, in the point 5, which is impersonating browsers' location services permissions to get users' location, I'm going to show you a really neat trick with source code that you may use for red teaming engagements, because sometimes we don't even need to burn a 0 day to get unauthorized user location. Sometimes we can just use a feature, which is the best way to get the unauthorized access to the user's location. And I'm also tell you a funny story about Safari and the problem that was there, which allowed attackers to get your location without your consent. And then the very end of the talk, we're gonna sum it up. And because I don't want you to live, from this talk with a sense of, let's say, not knowing on how to detect such problems, how to detect such vulnerabilities. So there will be some recommendations also for blue teams. Great. So let's start from the privacy fundamentals. All the privacy framework is turned on only when system integrity protection is turned on. And SIP is based on sandbox kernel extension, and it restricts access to many directories on macOS, but not only directories. In Apple community, we call SIP as a rootless thing, because even if you are root on macOS, you cannot do everything you want with your operating system. SIP is a kind of jail that is put on you as a user. So, and system integrity, because it's a sandbox kernel extension. So even if you think you are not sandboxed, even if you think your application is not sandboxed, in theory, we all live in hallucination, So every application on macOS, even though the operating system tells you that it's not sandboxed, it is sandboxed, because if system integrity protection is a default configuration, it's turned on. Great. So now let's talk more about transparency, consent, and control, which stands for TCC. So the main point of TCC is to protect your privacy as users. And Apple wanted to make sure that you give a certain application the clear consent that this particular application, will be able to access the data. So even if you are root, even if you escalate your privileges, you should not be able to bypass this prompt. If you can do so, please contact me. That's a vulnerability. And from macOS Ventura, TCC will also protect containers of sandboxed apps. So probably if you come from different platforms, you understand sandboxing as a as a kind of jail in which your application cannot escape to access resources that should not be available from the sandbox, right? But on macOS currently, on new macOS versions, it works both ways. So if an application is sandboxed, it means that also other applications should not be able to access data that your application stores. So it works now in both ways, right? You cannot do certain things from the inside, but also the environment could not interact with you as an application. That's, of course, the ideal world, which is not always ideal, but this is the architectonical decision. So if you, for example, try to, as you can see here on the terminal screenshot, if you want to, in this example, access data stored by Microsoft Excel, you can see that there's a container subdirectory. You will see that terminal will be asked you as a user that you want to access data from other apps. So this is another TCC protection, right? This unboxing. That's really important to understand before I dig into the allocation services. And the amount of data and the amount of resources that is protected by the TCC is still growing. It's not like it was 5 years ago when there was like a 5, 6, 7 things that was protected by TCC. Nowadays, there is a lot of different things protected by the TCC. And TCC really grew because it's even that granular that, for example, in automation TCC permission, you can specify what application should control what other application. So it's really granular. From our reverse engineering perspective, TCC stores all the permissions in SQLite-free databases. And there will be one SQLite-free database for everybody, which is this one. And each user on macOS will have their own TCC database located in their directory. And the idea was that, for example, you have 2 users using the same macOS, and one wants to give the browser access to your location, for example, but the second one is, a privacy-aware person and doesn't want to do so. So that's why there will be separate databases per each user on macOS and one global for like global permissions. If we open the SQLite-free database, we'll see something like that. So we have a service, which is a constant string determining on what actual service user granted the permission, the client that the permission was granted for, our value, of course, stands for if it was accepted or denied, and code signing requirement. That's an important thing. So for some of them, there is null, but for some of them, you have quotation marks. And the quotation marks appear in here because that's a binary form. And because it's binary form, it's not an ASCII thing, so it could not be displayed in here. But if we base64 encode the code signing requirements and use this code, we can transform the code signing requirements into a human readable version. And as you can see, it's pretty clear on what is being checked. And we're gonna focus on that later. Great. Now let's focus on location services. So even though there is the KTCC service Liverpool, the service constant string you can see in the SQLite-free database, on macOS it is not respected. So even if you think, so there is a service name for the location access permission, it will not work on macOS. In practice, the daemon which is responsible for location is not the TCC daemon, which is responsible for all the other TCC operations, almost all the other TCC operations, but user libexec location daemon. And location daemon does not respect the TCC database, but it respects a client Pelis database. So it's a completely different format, right? Pelis is an XML file, and the previous one, the TCC database, is SQLite-free. File, so there's a different attack service, for example, for parsers of those databases. And how can we access the location in a normal way? So if your application is sandboxed, So meaning that all the applications downloaded from the App Store, they are sandboxed. So they will, I mean, macOS will require for that applications that are sandboxed to have an entitlement, which is Apple Security Personal Information Location, entitlement to even ask location services for users' permission. So without that, the application would not be even able to ask the user for the location access. And in the info palist, an application must contain an entry which is called NS location usage description to tell the user why the location access is actually required for. However, if your application is unsandboxed, so for example, you download it directly from the internet and developers didn't tick the sandbox enforcement, and the hardened runtime is not turned on, you don't have to include any of these. So if you are doing a red teaming engagement and you need to retrieve user's location, that's a good trick to know. The code that makes the application asking for the user's location is like this. It's not really complicated. And you can ask the user for 3 different location access. So you have when in use authorization, always authorization, or temporary full accuracy authorization. And I think I don't need to explain that because it's pretty easy to understand, right? Great. So now let's talk more about the attack surface for location services. Firstly, we need to open the database to understand what is actually stored within that database. So we will see that we have multiple entries because, yeah, we have multiple applications on macOS installed, so there will be multiple entries. And let's focus on this particular one. Let's copy it and see what is actually stored in the database. So let's take Firefox example. And we'll see in that palette that for Firefox, location services store bundle identifier, which is bundle identifier, just a string, executable path, bundle path, which is the path to the main applications directory, and the requirement, the code signing requirement, the very same we observed in TCC database. Great. So now let's think, what can be tricked? What can we impersonate? Actually, almost everything. So bundle identifier, which is a string, and we sign our application with the bundle identifier we choose. So we can even create an application that will be starting from Apple our app. It's absolutely not verified by the operating system. Now let's talk about executable path and bundle path. Well, sandboxed applications will have those directories protected, but unsandboxed applications will not. And as browsers are not sandboxed, and there is a lot of applications on macOS that are not sandboxed, we can simply, replace the binaries, the files that are within these directories. So there's not a problem. This is not a problem at all. However, the fourth thing, which is the requirement, theoretically secure. Many different security mechanisms on macOS use the code signing requirements, so we treat it as it was a secure solution to verify code signing signature. Okay, but let's verify what is actually checked, because this is what is written into the database, what is saved by location D. But what does the location D actually check? Let's do a simple experiment. So we have our Firefox with location services granted, of course, and we copy and paste it to temporary directory. So now on one macOS, we have 2 different instances of Firefox. They are ideal copies, but they are in 2 different places on the file system. Well, let's open them both and see in the logs generated by the location D what's happening. So we can see that, all right, Firefox bundle has been launched, and private TMP Firefox has been launched. And for both, we get information that client authorized for location, starting short. So for both, location D granted location access, right? So Modified bundle path and the executable path do not matter for location. So those two things are completely not verified by location D, which means that with the techniques that I'm going to show you in a moment, we can also target the sandbox applications because we cannot modify the directories, but it doesn't matter because location D doesn't even check for that. The thing that is actually checked is the code signing requirement. But is the code signing requirement really secure? It is used by many different security mechanisms on macOS. So let's see how the code signing requirement is built. So this is the code signing requirement of Firefox. We can see the bundle identifier, which we know we can impersonate. Ensure Apple generic, which means that it has been signed by a certificate issued by Apple. So if we buy a paid developer account, we'll have such a code signing certificate. So that's also a thing we can bypass. But here comes the problem because the certificate leaf subject organization unit and this strange string organization unit is our team ID in practice. So we should not be able to impersonate that. I'm sorry. However, is that really a problem? Because if you can see, the code signing requirement does not verify version of the application. So all the kinds of downgrade attacks will come into play in here, right? So we can just take an old version of the application we target, which has no code injection blocking techniques enforced, and we can just, execute code within the context of the application we target. Code signing requirement will remain the same, and we can just perform a typical downgrade attack. How can we see if we are able to inject to a targeted application? Well, just by using a code sign tool, which is a built-in tool into macOS. Here we have an example on Keeper Password Manager that they allowed for code injections. If you want to read more about code injections, I created a large post about it on my blog, so feel free to visit it. Great, so to give you the better understanding, on the right, we'll be having the code signing requirement, and on the left, the different scenarios. So we have an up-to-date application with hardened runtime enabled, which blocks code injections, an old application without hardened runtime enabled, and the old application, the very same application, without hardened runtime enabled, but with our dynamic library injected. You will see that macOS will recognize them as an application with the same code signing requirement. So that's why we are able to perform the downgrade attack for all the location services things. So there is an architectonical problem in general with location services. That's not even a 0-day. That's a thing that Apple already knows for past 5 years, I think, because I reported the very same thing for TCC and still it still works. So the typical responsibility problem also exists in location services, because if our application A spawns application B, the application B will inherit the permissions of applications A. So if you are able to spawn another application as a privileged application, you inherit its permissions. I made a DEFCON talk 2 years ago about that, and I released a tool which is called Electronizer. Basically, mostly every Electron application was vulnerable at that time for that attack, so you can still use this technique. But what if we are interested in non-accurate location access? Some different typical techniques, IP address, region settings, time zone, Apple local, etc. However, the problem is with Wi-Fi SSIDs because it stopped working in macOS Sequoia. So you can see it's now being reducted, even if we use our Apple built-in tool. We trigger it directly from Objective-C code, it will be also reducted. So Apple really wanted to make sure that you cannot determine users' location based on SSID and SSID of Wi-Fi networks. And you will see that there is the location service disabled for non-entitled clients. So they probably introduced a new entitlement, which is private thing to Apple. So without that, we cannot access it. Great. So now let's talk about the vulnerabilities. The first vulnerability is really easy, actual two vulnerabilities. Accurate user's location was disclosed in logs, and it was disclosed by Weather app or Weather widget, because Weather needs to know your location to determine the forecast for the location you are in. So it must have the location access granted, and this is really easy. You just open the Weather app and the location was disclosed. Really easy vulnerability. The second one, again in Weather app, by breaking a route to weather data apple.com, Weather app was crashing. And in the crash log, it included the URL that it was trying to reach. And of course, the URL, here's the URL contained the location data. Again, a really simple vulnerability. This is the new one. There are applications like Weather, like Maps, like Find My that need to have the location access granted. But they did not have at that time certificate pinning. So we were able to create a proxy and just sniff the location. Right? A really easy thing, but there is one problem. Adding a trusted certificate, because we still need to present a valid TLS certificate, right, to those applications, made macOS to generate a prompt. And we want to operate in a stealth mode, so we want to bypass this prompt. However, there is a command called security authorization DB, in which we can interact with vardb audb, which is yet another security database on macOS. However, with that built-in tool, which is a feature, we can interact with it, and we can tell operating system, okay, macOS, for adding new trusted certificates, we don't want the user to give it the permission. And that's totally okay, that was a feature at that time. So this is how we were able to get access to user's location by just setting up a TLS proxy with a trusted TLS certificate. So here you have the old commands and a proof from Burp Suite that we were able to get the allocation from Find My application on macOS. Great. Another vulnerability by CF Network Diagnostics. So there is a very old framework, CF Network, which is mostly in every application because it's linked directly by the Foundation framework, which means that all the applications written in Objective-C that use the standard network API will respect this CF Network Diagnostics variable. And we just need to set it to 1 and observe in the logs user's location, because all the network requests were logged to the console log. Funny. There is a whole series of exploiting GarageBand and iMovie I made on Typhoon. Generally, iMovie and GarageBand allowed for code injections, and both of these applications have the private iCloud account access entitlements, which allowed me to get the iCloud tokens. And with iCloud tokens, I could just generate my session to the iCloud and get user's location directly from the iCloud by asking the Find My service. Let me show you the demo. So I pass one of those tokens. I'm refreshing in the background, Find My session. And my location is dumped directly from Apple servers. Really easy. Okay, now let's talk about impersonating browser's location services permissions to get users' location. Because when we do red teaming engagements, we don't want to burn 0 days, as I told you. If there is another way on how can we do it easier, we choose the way. So browsers usually have location services access granted as user wants to use Google Maps, dating apps, food ordering maps, etc. So probably everybody in the audience, I think, have at least one browser that has the location services access granted. And browsers are not really well known for isolation. So we can just, and this is a feature, that's not a vulnerability I'm showing to you right now. That's totally a feature. So we can instrument the browser to execute our JavaScript code within a domain we choose. So in here, I'm targeting the newest version of Google Chrome to open Chrome settings, which is a special URL, which will not generate any additional prompt. And we execute a JavaScript code that just gets our location. That's a feature, not a vulnerability. Just for your information, or at least now it's not treated as a vulnerability. The code is very simple, looks like that. So this presentation will be available online after my talk, so you can copy it directly from the talk. However, what about Safari? On Safari, unfortunately, that's not gonna work. Apple knew that location services and the TCC stuff is really important to the user, so they blocked they blocked the debugging features in Safari. You need to turn Safari to developer mode if you want to interact with Safari in that way. But there was a vulnerability which is triggered by web archives, I found. And web archives are just zip files. Zip files of a cached website that specifies the HTML code and the URL of the website that has been cached. So let me show you the demo on how it worked. We can see that the location is granted to Google Maps. Now let's see the content.html. Really simple, just a script that dumps the location. Now the web archive, here's the base64 version of that, the Google.com web resource URL, so the domain for which the Safari will think that it was cached. And if we open the web archive, the location is dumped. So we're able to impersonate Safari's like Google Maps HTML code. Great. So let me sum everything up. So location services, as I presented, they are a different privacy system. They have different permissions database from the TCC. The TCC had SQLite-free databases. Here in location services, we have a plist that contains everything. And the pillars have the same problem that the SQLite-free TCC database, meaning, I mean the code signing requirement, which has some architectonical problems, so all the downgrade attacks will work. If you have Electron applications installed on your machine and they are vulnerable for Electronizer, the tool I released on DEF CON, you are also vulnerable to impersonating to getting access to the unauthorized user's location. DILIP injections also lead to location services permission impersonation. So you want to detect DILIP injection tricks. Browsers can be instrumented. That's the easiest way. So if you work in a blue team, you may be interested in detecting Selenium unloading third-party plugins to the browsers. And I promised you that I will elaborate on the course I made. So this is a course for iOS developers and pen testers that want to build or pen test secure iOS applications. Of course, for Black Hat community, there is a discount. So if you want to have one, please contact me. And yeah, that's everything that I prepared for today. Thank you very much for your attention.